Hi everyone, this is the video to go over the solubility experiment for this week. So the first thing that we are going to consider in organic chemistry lab is we'll often be dealing with lots of different materials that look very similar. So you should never throw anything away. Don't consider anything as waste until you are sure of its identity and you are sure that you do not need it at the very end. And sometimes it's difficult to know if you have saved the right portion of your material. So it's often a good idea not to throw anything away until the end and to very clearly label everything so you know what is what. Almost everything is recoverable in the organic lab. It's difficult to actually lose the material unless you throw it in the waste bucket. At that point, then we cannot get it back. Okay. This week we are going to work on several experiments, and the following techniques in your Pavia textbook will be using these techniques in the experiment. So it's important for you to be familiar with these. So read through this before you come to lab. Technique 2, Technique 3, Technique 5, and Technique 10 in your Pavia book. These are in the back of the book. Okay, first we will work on pipette calibration as our first experiment. So we talked about this briefly during our discussion last week in lab. And so we're going to calibrate one short stem and one long stem past your pipette. And by calibrate, what we mean is we're going the past your pipettes, if you remember those disposable glass pipettes don't have any marks on the side of them. So when we're using them to measure volume, we don't really know how much volume that we're using. And so we're going to use tape to mark the height. Then we will know exactly when there's, for instance, 1 ml of liquid in each of those pipettes. Only a title and procedure are required for the pre-lab for this exercise, although if you had already written the purpose, we had gone over that, remember last week. It was just 1 or 2 sentences, very short, about what we're doing, why we're doing, how we're doing it, and how we'll know that we did it right. Read all of experiment 1. Okay, we're going to also do a couple of other experiments about solubility. Experiment 2 from your book, parts A, C, and E. So we're going to skip part B and we're going to skip part D. So when you read through experiment 2, you don't need to include parts B or D in your pre-lab. There's also a couple more experiments. Solubility exercise 1 and 2. There are handouts on Moodle, so these are not in your lab book. We're going to treat those handouts as if they are pages in your lab book. So what I mean by that is that you still have to write a pre-lab for these solubility exercises, even though we're going to have handouts instead of the information coming from your book. So write your title and the purpose and the procedure for these experiments as well. Solubility. So you are likely familiar with this concept from Gen Chem. I posted a video on our Moodle page right next to this one about with links to a video about solubility, the theoretical concepts of solubility, to kind of give you a review if you're a little shaky and you feel like you need a refresher on that. So check out that video if you feel like you need it. So we'll briefly talk about solubility in this video, but not in any deep detail. So if you feel like you don't remember intermolecular forces very well, you feel like you're a little bit shaky on polarity and electronegativity, maybe you should watch through those videos. Okay, so solubility is the extent to which a solute is soluble in a solvent. The extent to which a solute dissolves in a solvent. So when we're talking about solubility, we usually, that word is applied to the example where we have a solid material, like a solid powder, for example, and we dissolve it into a liquid solvent. So solubility is usually, we have different words for mixing different substances that are in different phases of matter, solids or liquids or gases, for example. And so usually when we talk about solubility, we're referring to the solute as a solid. So there are 3 possibilities. A solute can be completely soluble, and we usually would define that as being greater than 40 milligrams per mil at room temperature. It can be partially soluble and that's kind of a range that's just kind of less than 40 milligrams per mil, or it can be insoluble, in which you can't visibly notice that any of the solid has dissolved at all. And so these are kind of subjective. Of course, we can measure the amount that has dissolved, so we can determine if we're at soluble or partially soluble. But usually the way you can tell this is if something is soluble, the solid has disappeared. It has completely disappeared into the solute. Like when you dissolve sugar in water, you can no longer see the sugar depending on how much you're trying to dissolve. If something is partially soluble, then after you mix it, some of the solid will have disappeared, but some of the solid will remain. Again, depending on the amount of solid and the amount of liquid you're using. Then if something is insoluble, you usually don't see any visible difference between how much powder you put in and the amount that remains in the liquid. None has disappeared. None of it has dissolved. So it's kind of a subjective call when you're making this call. Soluble is pretty easy. Whether something is partially soluble or insoluble, you'll discuss that with your partner when you're completing these experiments. When we're describing when a liquid as a solute dissolving in another liquid as a solvent, we usually use the word miscibility. So miscible and soluble are similar terms. So again, soluble is usually applied to solids and miscibility is usually applied to liquids. Although you can still use the term solubility to describe the mixing of liquids as well. That's still appropriate. So the definition of miscibility is the solubility of a liquid solute in a solvent. And so the substance, the solute, and the solvent are both liquids. Liquids that mix completely in all proportions, we call them miscible. So what that means is if I take ethanol and water, I can make a 5% solution of ethanol in water. I can make a 10%, a 20%, a 38%, a 49%, a 94%, anything. Any proportion of ethanol that I put in water will dissolve completely. So if we can mix together two liquids and they will completely mix together in all proportions, then we call those two liquids miscible. And so miscible kind of sounds to me like mixable, right? So it means those two liquids are completely soluble in each other. When things are immiscible, that means that they do not completely mix together. So we have this, there's only two distinctions here. You can either be miscible or immiscible. When we're talking about solubility, we can have something that's partially soluble in the middle, right? There's soluble, insoluble, but then there's a term in the middle, partially soluble, and that's okay if something has kind of dissolved. When we're talking about miscibility, there is no in the middle. They either completely mix together in all proportions, or they don't. And so this is either an all or nothing kind of distinction. We don't have partially miscible. So when you're doing your experiments and you're trying to determine if something is miscible or immiscible, then you're going to have to determine if they mix together completely in all proportions. And if they don't, then we would classify them as immiscible, even if they did mix together in some proportions. Okay, consider, are ethanol and water soluble? Do they dissolve in each other? Are ethanol and water miscible? How do you know? So think about this. Think about the structure of ethanol. Think about the structure of water. Think about how they might interact, how their atoms would interact, what intermolecular forces they might be exhibiting, which of those intermolecular forces is the strongest, and if that interaction between those substances is enough to qualify them as being soluble or miscible in each other. So consider these questions as we move along. Taking into consideration ethanol's miscibility with water, remember we mentioned earlier when we were discussing miscibility that ethanol and water indeed are completely miscible. So the way in which they're going to interact, oxygen, water has an oxygen and a hydrogen. It has these two OH bonds, and so it's capable of exhibiting hydrogen bonding, right? Ethanol has one OH bond, and so it also can be a hydrogen bond acceptor and a hydrogen bond donor, just like water. So the CH2 and the CH3 part of ethanol don't contribute to the hydrogen bonding, but they also don't disrupt it. So ethanol and water can mix together completely in all proportions, even though ethanol only has one of those OH bonds, and it has that part, that CH2, CH3, that's not contributing to the hydrogen bonding. So considering that, would you expect methanol to be miscible in water? Methanol has one OH bond, and it has a CH3, so it has a smaller carbon-hydrogen part than ethanol. So what do you think about methanol? Would you expect it to be completely miscible with water in all proportions?
Probably not.
Would you expect methanol to be more, less, or equally soluble in water in comparison to ethanol? So again, considering what we were just discussing about their structure and the way that their intermolecular forces are going to interact being the main factor that decides solubility, consider whether the similarity between ethanol and methanol, and if that similarity is going to allow them to be miscible in water, and to the same extent, methanol to be miscible to the same extent as ethanol. Explain your reasoning, taking into consideration your answer for ethanol solubility in water. So think about that. This is going to be a part of your lab reports every week, is going to be to comment on these theoretical aspects of how this works. If ethanol is miscible because of its structure, because of the way it hydrogen bonds with water, would you expect methanol to be? Be able to explain that in a few sentences using the terminology that we're discussing here in your lab reports. Okay, some common organic bonds. Remember, most organic molecules are made of, for the most part, 4 common elements: carbon, hydrogen, nitrogen, and oxygen. Sometimes there's a halogen in there, right? Chlorine, fluorine, bromine, iodine. Sometimes sulfur, phosphorus are components of organic molecules. But for the most part, it's carbon, hydrogen, nitrogen, oxygen. Those are the 4 main elements that are in organic molecules. And so of those 4 elements, here are the following polar bonds: oxygen, hydrogen, nitrogen, hydrogen, carbon, oxygen, carbon, nitrogen, and carbon to a halogen. Nonpolar bonds are carbon, carbon, and carbon, hydrogen. So it's easier to remember the nonpolar bonds, right? We can pretty much say all the bonds in organic molecules, most of them are going to be polar, but the ones that are never polar are carbon-carbon bonds and carbon-hydrogen bonds. Because remember, the difference in electronegativity between those 2 atoms is too small. So if you're shaky about electronegativity in those distinctions, remember we say that an electronegativity difference between 0 and 0.4 is nonpolar. A difference between 0.5 and 1.9 is polar. And when the electronegativity difference is greater than 1.9, it's generally an ionic bond. So review those concepts if you're a little bit unfamiliar with that, because it's very, very important in organic chemistry. That's where we start at the basis of organic chemistry, is understanding the polarity between different bonds in organic molecules. Okay, so molecular polarity. Well, there's no words on this one. What the hell's going on here? Okay, there's supposed to be text on this. I don't know if you can see it. I can't see the text on my screen. So I'm going to read the text that should be on this one. So we know when a bond is polar because we can look at those electronegativities, right? Carbon and nitrogen has a difference of 0.5. That makes it polar. Carbon hydrogen, that has a difference of 0.4. That makes it nonpolar. So we can determine using that system whether a bond is polar. But what about a molecule? Molecules are made of lots of bonds. Well, in general, if a molecule has one polar bond, at least one polar bond, then it's usually a polar molecule. Polar bonds usually make polar molecules. That's not always true. There's some exceptions if there's symmetry. And maybe you might recall some of those from Gen Chem. If we have symmetric polar bonds that are exactly the same atoms and the same difference in electronegativities, and they're perfectly symmetric, then their dipole moments might cancel out and still lead to a nonpolar molecule. But that is the exception. So in general, polar bonds produce polar molecules. Okay, I think I see how this works now. I have to push forward to get the text. Exceptions. Polar bonds are a small part of the entire molecule. So if we have a really, really big molecule and the polar part of it is small, and let's say there's one polar bond, but there's 30 nonpolar bonds. If there are 30 nonpolar bonds in a molecule and only one polar bond, then that entire molecule is likely nonpolar. It will probably exhibit nonpolar properties because the one tiny polar bond in the molecule is not enough to overcome the 30 nonpolar bonds. And as I mentioned before, if we have symmetry in the molecule and the bonds are made of the same atoms and the same electronegativity difference, there's a possibility, depending on their molecular shape and their geometry, that those dipole moments will cancel out, leading to a nonpolar molecule. That is typically rare, though. That's the exception. So there are 3 intermolecular forces. Remember, there's dipole-dipole, and that force is exhibited when we have a polar bond that is not capable of hydrogen bonding. So if a bond is polar, but it does not contain OH, NH, or FH, then that bond is going to exhibit dipole-dipole intermolecular forces. This is a weak intermolecular force, but it's still stronger than London dispersion or van der Waals that we will talk about next. The other polar intermolecular force is hydrogen bonding, and that comes from OH, NH, and FH bonds. So notice that FH is not listed here, even though FH bonds do produce hydrogen bonding. And the reason is because there's only one molecule that has an FH bond, and that's FH. Remember, F can only make one bond, and H can only make one bond. So the only time that H is ever bonded to F is in the molecule HF. And so it is true that that's a hydrogen bond, but there's only one molecule that does it, and it's not organic. So the organic bonds that are capable of hydrogen bonding are OH and NH. That's the strongest intermolecular force. The nonpolar intermolecular force is the London dispersion or the van der Waals force. So remember, this is an intermolecular force that all molecules exhibit. Everything has a van der Waals force. Nonpolar molecules have it. Polar molecules have it. Everything has van der Waals. So this is a very weak force. However, when this very weak force is applied billions and billions and billions of times, it can actually be pretty strong. So the way that geckos can crawl up walls and walk on the ceiling is not because their feet are sticky in the sense that they feel like glue or tape or something. They're not sticky in that sense. They don't have any, there's no adhesive stickiness coming out of them. They're not exuding anything sticky from their paws. The way that they work is that they've got these little tiny hairs. You can see here we've got when you zoom in on their fingers, they have this very specific structure on their fingers. And when we go from B to C, you can see that those structures are made up of kind of pillars. They look like little hairs, right, in C. And then when we go from C to D, if we zoom in on each one of those structures, we can see that each one of those towers in C is actually itself made of several tiny hairs in D. And then if we look at D and notice how E is kind of zooming in on part of D, then we can see that E is made up of little tiny hairs. And then if we zoom in on E, we can see that even those little hairs in E are made up of even smaller hairs. So the point is that each one of those little tiny hairs exhibits a van der Waals force. And by itself, that one van der Waals force is very, very weak. But when you have 1 trillion of them on each finger, then they add together and the force becomes strong enough to actually allow that gecko to walk up the wall or to walk on the ceiling. So the van der Waals force is weak by itself in between two particles, but when you have it over trillions and trillions of particles, then it can exhibit a pretty substantial force. There is a link in the slides. If you click on the slides in the Moodle page, you can find this one and click on this link and watch this video, especially the parts between minute 128 and 438. Okay, so let's talk briefly about the difference between covalent bonding and intermolecular interactions. So covalent bonding is the bond that holds atoms together. So when we look at water, we have O and two H's, right? We have two OH bonds. The bonds that hold the water molecule together, those bonds between the oxygen atom and the hydrogen atom, those are covalent bonds. They are the parts that hold the molecule itself together. But when I have two water molecules and I bring them close to each other, they also are sticky to each other. And when they stick to each other, those two water molecules, they're not sticking to each other through covalent bonds, right? They're sticking to each other through hydrogen bonds. And those hydrogen bonds are intermolecular interactions. So it's important to think about the difference between the way that atoms stick together in a molecule and the way that molecules stick together when I have a lot of them. Because covalent bonds are very, very, very strong, and intermolecular forces, by comparison, are very, very weak, right? It's easy to break intermolecular forces. I just have to heat up the water, right? If I heat water and it starts to boil, then I've broken the intermolecular forces. But even if I boil water, I'm not turning it into something other than H2O. The bonds between the oxygen and the hydrogen, those covalent bonds, don't break when the water boils. The water molecules break apart from each other, but the oxygen and hydrogen atoms do not break apart from each other. Those covalent bonds are very, very strong. Okay, so remember the golden rule of solubility. This is very, very, very important. Like dissolves like. Solvents will dissolve in a solvent with similar polarity, right? When I have a polar substance, it will dissolve in a polar solvent. When I have a non-polar substance, it will dissolve in a non-polar solvent. So like dissolves like. Non-polar and polar don't mix. They don't like each other. So in this case, opposites do not attract. So like dissolves like. They need to be the same polarity. Recitation question 3. What is the major intermolecular attractive force between methanol and water? Do you think it's van der Waals, dipole-dipole, or hydrogen bonding? And consider this as well. Which of those intermolecular forces is methanol capable of displaying? Does methanol display van der Waals? Does it have dipole-dipole interactions? Does it have hydrogen bonding interactions? And of those, which is the major intermolecular attractive force between the methanol and the water? Consider, is one octanol miscible with water? So notice the difference between all of these structures we've been looking at so far. We looked at ethanol, right? Ethanol has a CH2 part and a CH3 part, so it has two carbons, a 2-carbon tail. Methanol has a CH3, so it has a 1-carbon tail. And then octanol, if we count these vertices, we have 1, 2, 3, 4, 5, 6, 7, 8. So octanol has 8 carbon tail. They all have OH. They all have a 1 OH group, but they have a 1-carbon tail, a 2-carbon tail, or an 8-carbon tail. Think about how the length of that carbon tail might interfere with the way that these molecules interact. So water can interact with other water molecules very well because they have 2 OH groups on each side. They can surround each other. Methanol can react with water pretty well too. It's got a CH3 tail on one side and an OH on the other, but that CH3 tail is pretty small. It doesn't interfere with the ability of that molecule to hydrogen bond. Ethanol has a CH2 has a 2-carbon tail, and we know that ethanol is miscible in water. So ethanol has 2 carbons, and they do not interfere with ethanol's ability to hydrogen bond with water. So if I mix octanol and water, what do you think would happen? It has 8 carbons in that chain. Do you think it is able to mix with water or not? So in recitation, I would have had some octanol and some water and mixed them and showed you they don't mix. Octanol floats on top of water. Octanol is not miscible with water. It's not even soluble in water. They don't mix at all. Octanol is completely insoluble in water. Why do you think that is? It still has an OH. It has a much longer carbon tail, 8 carbons, but it still has an OH, which means it's still capable of hydrogen bonding, right? So why is it that octanol can't mix with water, but ethanol and methanol can? So think about that. Provide a reason for one octanol's behavior in water. Miscibility in this case meaning it's immiscible, right? So octanol's immiscibility in water. Okay, the experiments, again, that we're going to be performing will determine the solubility of solid compounds of different polarities in solvents of different polarities. So we'll have some solids that are polar or nonpolar, and we'll have some solvents that are polar or nonpolar. And we will apply the rule of like dissolves like, and we will figure out which of these substances is going to dissolve in which of these solvents due to their similar polarity. We will determine the miscibility of pairs of solvents. So we'll do the same thing that we did with the solids, but we'll do it with liquids. We'll have polar liquids, nonpolar liquids, and we'll have different solvents, so we'll try to mix them together and see if they're miscible or immiscible. Remember, when we're talking about solubility, we have soluble, partially soluble, or insoluble. We have 3 choices, but when we talk about miscibility, we only have 2 choices, miscible or immiscible. We will next determine the miscibility of alcohols in solvents of differing polarities. So we've been just kind of discussing this thought experiment all along. Does methanol dissolve in water? Does ethanol dissolve in water with 2 carbons? Does octanol dissolve in water with 8 carbons? So those are alcohols. So we'll determine the miscibility of alcohols in solvents of differing polarities. And finally, we will determine the miscibility of alcohols in water. Experimental advice. Clearly label all tubes with a wax pencil. Do not use label tape. The label tape leaves sticky adhesive all over the tubes that is a pain in the butt to clean off. The wax pencil is easy to clean off. Pipette bulbs are reusable. The little rubber bulbs that go on the end of your pipette, do not throw them away unless they are hard and or cracked and they in general don't work. We will use them until they no longer are useful. Please do not wash them and try not to suck up any solvent in the bulb. Be very careful when using your pipette and hold the solvent inside the glass part of the pipette. Do not suck the solvent into the rubber bulb. That's how they get ruined. You will be working with very small quantities, so observe carefully. Note that solutes can be partially soluble, but solvents cannot be partially miscible. It's either miscible or immiscible. It's all or nothing. Experimental details and advice. You will be working with a partner for all experiments this week. You can and should discuss observations with all of your lab mates. So generally we will be working by ourselves in lab, but this week you will have a partner and you will be discussing your observations together about what you are seeing. Because remember, some of these are subjective. And so you will have a discussion with your partner about whether they are soluble, partially soluble, or insoluble, depending on what it is you're seeing. Standard glass washing procedure. Soap and water, distilled water, and then acetone. So first we'll use soap and water to get all of the bits out, if there's any insoluble pieces. And then we will use distilled water to rinse all of the regular water off, the tap water off. And finally, we will rinse the distilled water off with acetone. So it goes soap water, and then tap water to rinse the soap off, and then distilled water to rinse the tap water off, and then acetone to rinse the distilled water off. That's a good way to wash your glass, because if you don't use distilled water and you just rinse with tap water, then you'll have ions, right? Because there's salt in the tap water. So if that dries in your glassware, then you'll have ions in your glassware that can interfere with your experiments. So that's why we use distilled water. And then we use acetone to remove the distilled water, because distilled water can take a long time to dry also. And acetone will dissolve the water, remove it very quickly from the glassware because it doesn't bead up, it coats the inside of the glass, and then the acetone evaporates very quickly. So then you'll have a clean, dry piece of glassware without any ions in it. Of course, before you wash your glassware, you need to dispose of any waste, right? And you do not dispose of the waste in the sink. You will first dispose of the waste in the appropriate waste container, as much of it as you can. Just invert the flask and dump it out and get as much of it out as you can. If there's a little tiny bit left, any pieces that are sticking to the side, that's when you use soap and water. That's when you go to the sink and start to use soap and water and rinse it out and then do this washing procedure. Do not use paper towels to dry the inside of glassware. You will leave dust in there. The paper towels are not necessarily clean. That's not a good way to dry your glassware. Please clean all test tubes used and return them to the appropriate location. Usually when we are using test tubes that are not found in our drawers, there will be a container of test tubes on the bench in the middle of the room for everyone to use. And there will also be an empty container that says clean tubes. So after you are finished with the experiment, you'll clean all the test tubes that you borrowed from the center and you'll return them to the clean tubes container. Clearly label all tubes with a wax pencil. As we mentioned, don't use label tape. Use medium-sized tubes for Pavia Experiment 2, Parts A, C, and E. Those are in your drawer. Use small-sized tubes for exercises 1 and 2, the handouts, and those are on the common bench area that I just had discussed. So some of the tubes will be from your drawer for Experiment 2, and some of the tubes that you'll borrow from the common area. Please place all waste in the solvent waste bottle in the hood in the instrument lab, Science 273, as we discussed last week. Okay, so we discussed how you should prepare your pre-lab, and even though you're working in pairs this week, you should still prepare your own pre-lab independently. So everybody needs to prepare their own pre-lab. During lab, students should write down all the data and observations in their own notebook and ink. So again, even though you're working with partners, fill out your own notebook. You have to be taking your own notes. Add these experiments to your table of contents. In your lab pages, write your name and date, title of the experiment, purpose, method paragraphs for all experiments, purpose for conducting experiments and the experimental methods to be employed, table of reagents as we discussed, detailed stepwise procedure as we discussed. Your notebook is your primary source of information. You may briefly consult your lab textbook during class if needed. So I had suggested you not bring your textbook to lab, or if you do, it should be in your backpack, and your backpack should be over on the backpack storage area. I don't think it's a great idea to leave your textbook on the bench while people are working. Having said that, if you do need to look at your book for a moment to figure out what you're supposed to do, then it's okay to go get it from your backpack and check it out and get the piece of information you need, and then I would suggest returning it to your backpack and not leaving it on the common bench area. Remember, we discussed this way that you have 2/3 of the column to write your procedure, and 1/3 right column is reserved for procedure changes, data, and observations, as we discussed last week. It is helpful to pre-draw your data tables. So if you can make your lab notebook, because remember I mentioned you're not going to print out your lab report and fill it out during class, but you are going to fill out that lab report eventually. So if you format your lab notebook to look like the lab report handout and all of the tables are constructed the same way, then you'll be able to easily copy down information in the way that it's required in your report. So make the tables the same way that you see in those handouts so that you can copy that information from your lab book into the lab report when you go to complete your lab reports. Please answer these pre-lab questions in complete sentences in your lab notebook. So in addition to everything we have discussed so far about your pre-lab, I would also like you to please include the answers to these pre-lab questions in your pre-lab write-up. Number 1, would you expect 2-propanol to be more, less, or equally soluble in water in comparison to 1-propanol's solubility with water? Explain your reasoning. Write down what you think. Number 2, what does the presence of turbidity or 2 different phases imply when mixing a liquid-liquid or solute-solvent pair? Turbidity means cloudiness. So what does the presence of cloudiness or 2 different phases imply when mixing a pair? Write down your answer to those questions in your pre-lab. Your pre-lab needs to be complete before you begin working on your experiments. So we have already discussed this. I'm going to check your pre-labs first thing when we get into lab, and if it is not complete and you haven't done your pre-lab, I can't let you do the experiment. So you must complete your pre-lab before we do the experiment. Again, even though you will be working in pairs, you must prepare your own pre-lab and you must prepare your own lab report. So you can work with your lab partner on the answers that are going to go into the lab report, but there are questions where you are asked to explain your reasoning. In those sections, I want your words. I don't want 2 partners to turn in the exact same sentences. I want you to each come up with your own answers when coming up with your reasoning. For parts of the post-lab that require data input, it's okay for your answers and your pair and your partner's answers to match, and they should, because you were both doing the experiment together, right? So lots of your report will look exactly the same, but not every part of your report should look the same. There should be parts that are done in your own words that are different. There is a report form to download and fill out available on Moodle. Download the document, type in the requested information, and print it out. Again, I mentioned before, you have to type in everything. You have to use Simics Draw or BioVia to draw the chemical structures and to put those into the Word document. It's very helpful to review the report prior to conducting the experiments. So even though you don't actually complete the post-lab until after lab, you should look at it before lab so that you know what is required of you. That way you can fill out the information in a way that is going to be the most helpful for completing your lab report. Note that you can type as much as you want in the lab report. The space will continue to expand. Make sure to staple copies of your top white lab sheets right side up and in numerical order to the back of your report. So I want the printed out document that you have typed in and put all of your chemical structures in with all of your answers. And I also want copies from your lab pages in order stapled to the back. Turn in your report to your lab instructor in the subsequent lab period at the start of the lab session. So at the very beginning of lab, I will collect your post labs from the previous week. Reminders and FYI, graded work will be placed in the mailboxes located next to Science 261 across from the elevator in the chemistry department. References. Wikipedia can be used as a reference because it's not formally referenced. So remember, as I had mentioned before, since we are going to be using Wikipedia as a way for us to find information about chemicals, the chemical safety data, the physical properties about our reagent table, that's okay. It's okay to use Wikipedia in that sense. If you are trying to find a formal reference from a peer-reviewed journal for information for a lab report, if a lab report requests a formal reference, then Wikipedia is not a formal reference. So that's what this means. Wikipedia is not a formal reference, so you can't use it if you were trying to cite information. If you're trying to cite information, then you need to have primary source from a peer-reviewed journal. But if you're using Wikipedia to fill out information in your reagent table, that's okay. Please do that. It's actually a very easy way to do it. Helpful handouts in the Moodle site that you should read. The plagiarism spectrum, significant figures in rounding review, measurements, significant figures in standard deviation, how to use an analytical balance, functional groups, common names, intermolecular forces. These are all documents that are available on the Moodle page that you will be expected to know the information in these documents, and you will be expected to apply that information in your lab reports. So if you're unsure about how to do some of this stuff, functional groups, common names, stuff like that, look at these before you turn in your lab report. Reminder, all handouts and PowerPoint slides are available online on Moodle. Read PowerPoint slides, handouts, book, footnotes for upcoming lab prior to attending the recitation, because again, as I mentioned, we will often have quizzes in recitation. Okay, that's it for this week. If you have any questions, please reach out to me by email. I will also be in my office Tuesday morning starting at about 8:30. So if you want to come see me in person, I'll be in there from about 8:30 to 9:30 when the first lab period starts. Send me an email, come see me. And otherwise, I'll see you on Tuesday.